You're now live.
Oh, thank you. Well, thanks for all coming today. Today I'm going to be talking about a project or paper that I'm currently playing around with Alison Heppenstall and Nick Mallison from the University of Leeds. This is a talk that we were thinking of giving, or that we gave at Rob's Agent Congress in November, but with some other stuff thrown into it. So what I'm going to be talking about today is basically why is geography interesting? What is the unique problems we're trying to simulate with looking at geographical problems? How good are we at representing space, representing human behavior, but also what are the main challenges we have with respect to building models of geographical systems? So what is the elephant in the room, so to speak? And feel free to ask me questions or comments as I go along, by the way. Also, how can basically we can use potentially big data with respect to modelling, and what are the headaches it's going to give us, but also what are the opportunities. But also this is sort of a reflection of basically how well have we done from an agent-based modelling perspective in the last 20 years with respect to building models of geographical systems. So traditionally in geography, most models were very top-down aggregate types of models. But now the focus has shifted from top-down models to bottom-up. You've all been indoctrinated in this through CSS programs, right? So you all know the pros and cons about individual models versus more aggregate models. In the geographical community, the most commonly used model is sort of spatial interaction models, looking at the flow of a good or a person from one place to another place. Normally we are basically trying to understand an area, say a crime rate, for example, based on some properties of that system, whether it's education, deprivation, number of young people, or disenfranchised youth, and things like that. And then we try to use this information to predict what is the crime rate going to be in a specific area. But we want to do it at the individual level, not necessarily at the top, from the top down. And the challenge we have is basically understanding the individual behavior and the movement of people through space, through time, and specifically, what are we interested in as modelers? We're interested in who, where things are happening, what's happening, and why are people doing what they do? Why do people decide to rob a house or burgle a house? I don't know what the American definition is. Burgle, if I say that, do you know what I mean?
Robbery.
Yeah.
Okay.
Where is when? It's who, 5 W's, who, what, where, when, why.
When? That's true.
Okay.
But yeah, also when, but that's for prediction. The question is,
You said prediction.
Did I?
Yes.
Damn it! I can roll this back now and check, right?
That's right.
So for you guys in the audience that are not here, that was referring to the guy running the YouTube channel. But I want, agent-based modeling and GIS sort of evolved from a certain book, believe it or not, which was Triggerscape and Rob's book. In that model, they showed how the terrain could impact many different things, right? The accumulation of wealth and things like that. But you also have some other key leading books in this time frame. And I'm trying to sort of tell a story saying, how have we advanced from the more traditional books, such as Growing Artificial Societies, or this one edited by Randy Gimlet from a series of workshops in Santa Fe in the early mid-1990s, integrating GIS into agent-based models, has moved on over time. We have a great review paper by Don Parker et al. Talking about the promise of agent-based modelling with respect to land use and land cover change types of models. We have the idea of Isaac Benison and Paul Torrance's book on geosimulation, how we can create the geographical automata, to study basically the world around us. We have some books with respect to cities and the growth of the way we've changed our thinking about cities from and modelling from very aggregate, very static styles of modelling to more dynamic micro styles of modelling. We have this excellent edited book by Heppenstall, Crook, and Backey and C, which is also sort of like a scene setting. If you don't like what I'm talking about today, if you just read the first 12 chapters of that book, you'll know all about agent-based modeling. And more recently, you have some other interesting books which are about understanding spatial patterns and how these emerge from individual interactions, to the work by Bill Rand and Wilskinsky, which is about using net logo, and also Batty's new book, or relatively new book, The Science of Cities, which is emphasizing the utility of networks with respect to understanding cities and how networks are everywhere. But there's been a growing amount of publications in this area, but literally how far have we gone? And hopefully, you know, we can explain this. Why are we interested in this? Geography is messy. Space is messy. Things move through space, through time, and we're trying to capture this movement of people through space and through time. So what I'm trying to show here is basically you have individuals. These individuals are connected. They can be connected to each other, or they can be connected to a place, or and they can also be in specific neighborhoods. People move through space, through time. New networks are formed. Networks dissolve, and new neighborhoods might emerge and things like that. You know, believe it or not a lot of people explore networks in agent-based models, right? You'll see them, and they tend to be very abstract. They just tend to be aspatial, no space in them at all. In the geographical realm, it's only in the last few years that we've actually started really incorporating real networks in models. Traditionally, in agent-based models, a network was your surrounding 8 neighbors, or some variation of that. Now people are explicitly capturing network dynamics inside the model processes, such as Bianca Perez, a former PhD student of ours here. But you know, capturing networks is a new thing that's not being done. Then you also got the multimodal networks, like multiple networks on top of each other, and connecting those together. That's something that's still being explored now. So, you know, we can build models. We can build models at any spatial or temporal resolution that we care about. You know, we are very good at pedestrian modeling. You might recognize this Yang's reimplementation of campus model in NetLogo. By the way, if anyone wants good NetLogo models, Yang's website, Geospatial CSS, is very good for that. But we build models at a whole variety of things, spatial, temporal scales. Nearly any problem that you're interested in is already probably being explored in this realm, right? But you know, the challenge of these types of models is, you know, you have either very abstract spaces or very geographical, very detailed spaces, using a lot of geospatial information in these models. And normally, as you go for longer time frames and also higher spatial scales, your models become less detailed, less geographical information is incorporated within these types of models. But what are we good at in agent-based models? I mean, we are really good now. There's been proliferation of data, especially spatial data, remote sensing, and things like that. We are very good at taking the world, slicing in a series of layers, and using these layers to build our artificial environment for our agents to live on, right? But the challenge is, inside of this, we have the people that are connected to each other, and how do they talk to each other? What causes them to do certain things? I think we're still lacking that part of agent-based modeling. I don't think, you know, we've advanced that much. As I say, we're very good at representing space. We're very good at representing certain types of processes, especially spatial diffusion. Urban growth models are really sort of well documented, like the work by Keith Clark. But these models come from the 1990s, cell automata styles of models. Here you're seeing Santa Fe, and the idea is you have the blue areas, which is the initial urban area. Red is potentially where new houses are going to be bought, or where land's being converted from, say, rural to urban, and you sort of see the spatial spread of these models. And you know, these models have been widely used. It's interesting with the sleuth model. I think it's had like 150 applications around the world, and it's one of the few models I've ever seen where they've gone back and you make a prediction it's going to be a land use pattern in 10 years' time. They've gone back to look at that in 10 years later to see if their predictions are correct or not. Have anyone ever seen that happen in the social sciences?
And their predictions were correct?
Good enough. Yes, but we don't do that in social sciences. We never go back and look at our is it even doing it. But there's sort of a balancing act within, and there's still a big debate in this, and I'll come back to this in a couple of slides later, which is how much realism do you need in the models? Do you want abstract environments like the shelling styles of models? Or do you want really detailed geometry, roads, rivers, and those types of things also in the model? Some people would say that simple toy models, as people would describe, say, the shelling model, like the traditional, basically nice because you can understand them. You can understand how the rules function and so forth. Often the argument for very simple models is that they're there purely to explore theory, and therefore, because there's no real geographical information in these models, apart from your surrounding cells, you're unencumbered by the complexities of the geometries. So, for example, you've all probably heard the expression living on the wrong side of the tracks with respect to neighborhoods, right, and school catchments. In these types of models, you don't have that issues. You don't have to incorporate the impact of geography on your modeling processes, which therefore makes them relatively easy. Some people might say that these abstract toy models are not applicable to the real world. So if you are a decision maker and someone shows you the shelling model, what would you say? You'd like, that doesn't relate to Washington DC, it doesn't relate to Baltimore, right? So therefore the question is, does adding a map make it better, make it more realistic or more applicable? And I sit on the fence and it depends on the purpose of the model, right? Some people say that GIS is more accurate representation of the world, so you can capture more types of phenomena. Some people would also argue by capturing spatial information, your models are more useful for forecasts or predictions of scenarios. For example, what happens if sea level rises by X? With an abstract environment, that's hard to know. With real world geographical information, you can see the impact of sea level rise and these types of things. But even when you start adding more and more information to them, I would say that the simulations are still not that easy to understand. And the question is, are they useful? Yeah, and because they are but the other idea here is that is the simulation easy to understand? Does it portray the real system? How do we gain confidence in these types of models? Because again, they are all model simplifications of reality. So where's the balance here? How do we come to this balance? So there's one thing that we always struggle with is how much realism do we put into models? And the challenge of realism, and also what is an agent and things like that, comes to the way we represent space. All of you know the idea of that neo-decomposability issues and subsystems and things like that, right? Especially people who just doing the comprehensive exams, because that's when you're But we have societies, we have neighborhoods, people here you can imagine these are different neighborhoods. We know people in the neighborhoods are connected. For example, you'll interact with your neighbors, potentially, or unless you don't like your neighbors, then you won't interact with them. But you'll also have some type of interaction with other neighborhoods. Say if your kid's on a soccer team, you'll then go to another area to play soccer and things like that. So everything's connected. But as we aggregate up, we lose some of the information at the individual level. So if you take these neighborhoods, aggregate them up, and just look at the aggregate sum, you miss what's happening at the individual level. Like census data. Census made up of the whole US population, but it doesn't give us much apart from the number of people living in the area, because that's an aggregation, right? And depending on how aggregate you go, it depends on how much information that we have. So the other challenge we have within these models is how much information do we want to represent in them? So traditional migration models work at this very aggregate scale, while a lot of, say, the pedestrian models work at this very micro scale of individual movements. But it's hard to represent a million people in a pedestrian model, because of you have all 100 entity agents interacting with each other. But at the aggregate model, you might have 100 entities, but they might be doing nothing at all, or they might not be interacting at all. So another challenge we have is, how do we break up the space around us and incorporate that in our models, and what connects the different spaces together? So that's another thing that we keep struggling with, and again, it's not really resolved. And when it comes to like ABM itself, like how has agent-based models progressed in the last 20 years? I would say, in general, the models that we've started creating can incorporate more data. We have more geographical data. Computational power is rising, so we can incorporate models. It's funny, the model I did for my PhD would take a week to run, right? Just one iteration of it would take 1 week to run. Now, the same model with the same number of agents in the same area takes about 20 minutes to run. And I haven't improved the code, it's just literally computational has just changed. We can represent more detail in models because of this, and therefore more agents. In the old days, I can't remember how many model agents were in the Sugarscape model, the original, but there's not many, right?
Yeah, a couple hundred.
Couple of hundred. Now you can easily do 1 million, 2 million, 3 million on a laptop, or on a whirring machine, like you hear in the background there, several, what is it?
120 million.
120 million, right? We have more tools and better visualizations of agent-based models than we did 20 years ago. Traditionally, they were slow. Traditionally you wouldn't have very good visualizations at all. And then now we can, easily visualize them with the GUIs that we have built into, say, NetLogo, Mason, Recast, and things like that. There's more tools for building agent-based models. So traditionally, the first models were written in whatever language the programmer you wanted to use. Then C++, when Swarm, Java, Smalltalk, NetLogo. You have this new one, Gamma, and things like that. So you have a lot of more tools available for building them. There's the book by Gimlet that I edited talks about coupling GIS into these types of models. The coupling tends to be either loosely coupled, where you just pass files to the model, then run the model, output the files, and analyze them in a GIS, or they can be very tightly coupled, where there's seamless integration between the GIS and an agent-based model. We are very good at coupling models together, but that hasn't really advanced much in the last 20 years. But we are still, we can, with more data, we can add more data into these models. As I already sort of said, we've got more software out there, got more and more data. There is something that I'm wondering still is how good are we, in general, of connecting our models to theory? And I say that is that a lot of time you build models. When you build models, are you testing a specific theory, or are you just creating your own ideas? Bill, what do you do?
I want to have theories that are referenceable and that the code implements.
Okay. What about when you're doing your 600 your class projects? What do you do? You don't even look at what's out there, right?
We don't even look at what?
Theory. What's out there, theory-wise, or model idea.
No, I've looked at theories for some stuff, not for my, like, maybe based on models, because when you read a paper that has a model,
yeah,
they then reference some theory, so then I go back and check what those theories say,
yeah,
and then come back to understand if they're doing it the right way.
Yeah, but a lot of time when you read the GIS models, there's no mention of theory in them at all. So the question is, why is that? Is that because people are more interested in developing the models, or ignoring the theory out there? Go on.
I feel like sometimes people who are more interested in who suddenly become interested in simulation because they think it's cool. I know but I think they want to be able to say, listen, I put together the simulation, and then the moment they accomplish that task, they almost lose a lot of interest in it, and think, let me go back to what I know, what I was taught in my PhD program or whatever, and they don't get into the framework and the methodology of agent-based modeling for a prolonged period. They just want to do one and walk away from it. They do the same thing with social network analysis too. They want to do one network thing and go back to what they were doing before.
Yeah. Is it also the lack of like cross-discipline stuff? So like you're in a GIS program, and all you're doing is GIS. So like trying to bring in like a political science or economics, it just seems like a bridge too far. 'Cause you're so locked on polygon lines and polygons.
Yeah,
and
no,
stuff.
that's the other thing is, that you want. I agree, and that's one thing I like about this place is that, now we have the theory of planned behaviour, which I never even heard of till I came to George Mason University, and they'll still, what?
I don't like it.
You don't like it, but we can test it in these types of models, though, right?
I don't know that there's a theory there.
Wait, that was
Data.
in the 70s, theory of planned behavior, right?
As
By
a-
economists and social anthropologists, right?
Yeah, but this,
Go on, Netta knows this stuff much better than anyone else.
I haven't spent a lot of time on that lately, so my memory's really fuzzy on the theory of planned behavior. I've been studying theory of disaster behavior, so.
I
Yeah.
have the original article.
But that's a mush of theory. There's a lot of theory
Yeah.
that gets
But-
integrated into one thing.
And then the
And
other.
I think, just for the record, I think theory of planned behavior is one of those kinds of things where a lot of theory gets rolled up into some broader application.
Okay. But anyway, theory. Do we, how do we connect it to ABM? I don't think we cover that very well. I think most of the time we just roll our own. Most people just roll agent-based models out, looking at what is out there in already existence. The other thing that the challenge that we have is, representing the scale of the model. What spatial scale do we want? We never think about what justifications do we have for representing the model at a certain resolution that we're doing it at. Also, what is an agent? I know that sounds stupid. Everyone's like, an agent's easy. It's a household. It's an individual. It's a car or whatever. But what happens if we change that? How would that impact the model or what we're trying to do, and also the dynamics within inside of this? And in these types of models, what is time? What is an appropriate unit of time? And often we assume residential land markets, for example, operate within months, years, while pedestrian models operate in seconds and things. But then we have if you want to connect a residential housing market model to a pedestrian model, what's a way of doing those two things together? Because you have the two different temporal processes there, also two different spatial processes there. So it's connecting these things. So I think we've made progress in some areas here, still areas that we can still explore and play around with, or explore. My pet peeve of agent-based modeling is human behavior. We always say in agent-based models we can represent human behavior, right? How do we go about representing human behavior? We have so this is the same, I'm going to switch it. So I'm going to have behavioral complexity. We have the simple threshold Schelling model. If a certain percentage of neighbours are like ourselves, we are happy. If not, we move to a new location, right? But then you have the real complex human behavior, what's going on inside one's brain. By the way, that is my brain.
Really?
Yeah, when I was a
Did
grad
that
student,
for
we used to
myself.
do MMRI
On your own
experiments.
brains?
Pardon? No, I
On
took,
your own brain?
no, not on my own brain. I was a guinea pig. I got $20 for like an hour's worth of work, which is a good value for money there, right? So let's think.
Where are I'm sorry. Where are the is it? Do you have
Where's
ones
the little
where
man?
it shows the lit up regions and stuff and?
none of them
No.
lit up.
No, no, it's all-
It's all dark. It's awesome.
Anyway, thank you for that, Bill. So here's the question, right? And then here I'm interested in basically the system environmental complexity. So here would be like the whole city in very fine detail, sewer lines, your underground electricity, or all the things that people that drive tanks through the streets are interested in. Here, abstract representations of space, right? So, if we take this slide again, which is basically the spatial scale, and the temporal scale, but this time we're going to switch them around to behavioral complexity and then systems complexity. So what I mean by system complexity, the more geometry, the more fine scale, the more details the model is, it's going to go up to here. The more simple representation of space is going to go down to here, right? When it comes to behavior, the simple models are going to be over here. The most complicated models are going to be over here, right? These are from a geographical perspective. I haven't talked about ACDAS or those types of things because they tend to be aspatial to start with, right?
True.
So this is purely from a geographical perspective. So let's rearrange these models and see where they all roughly all fit. So we've got the migration models are down here, abstract, very notional representation of space. Most models, I would argue, that we build in the geographical sciences, quite sad this slide I think, fit over here. We don't do a very good job of representing behavior. Most of these models will use threshold calculations. By the way, do you know what I mean by threshold calculations? If you don't, you should read chapter 12 in my edited book with Alison Heppenstall that Dr. Bill Kennedy wrote here, which is a must. It could have been a bit longer, but he kept it short.
Andrew, threshold calculation?
So Bill describes agent-based models as three different types of agent-based, ways of capturing behavior in agent-based models. You have the threshold models, which are good enough if you know how the system really well behaves, like the Shelley model. If a certain percentage of my neighbours are like myself, I'm okay. If not, I move. So you have a threshold. When I get to 12 or 20, when I get to 40, I die, so to speak. Those types of models. I was going to say 12, but I realise that's quite not very good. Right, those are the sort of threshold models. Then you have the next line of models, which are basically the cognitive architecture styles of models. So you have, and I'll talk about these in a little bit more, like the beliefs, desires, intention models, the PEX models, which stands for physics. I never know this one.
Physiological, emotional, social, and rational or cognitive.
Yeah, models. And then Bill's favourite, fast and frugal. But these fast and frugal, these are like decision trees. You can consider them as a series of if-else statements, or some type of intensity analyzer, and then you choose the thing that is what's driving you the most. But it's a balancing more. But then you have the real behavioural, more the rich. Is rich the right word?
Yeah.
The highest level would be the cognitive architectures, such as ACDAS or Clarion and things like that. Yeah. Okay. Yes? Which
Sure.
are literally modelling the brain. Remember, you've got modelling one person. But those models tend to be just one agent, one decision-making entity. So they're not used in the geo side because of that reason. It's just one person. So there's very few models that come over to this area. Most of the ones I've seen so far relate to criminology, crime. So the emergence of riots, Bianca Perez, or Nick Mallison uses it to understand burglaries and patterns of crime and things like that. The Brannigan and Brannigan's agent-based models use BDI and PEX type framework. Yeah.
And why is that?
I don't know. Even in your own fields, right? I'm having a rough guess. Nearly all the models you've done in class would just, unless you've done Bill's cognitive architecture class, cognitive modeling class, would be just simple threshold models.
But for example, I don't know if I can speak for Rob, but let's say that I can in Rob's model. Rob is a philosophical believer in simple rules.
Yes.
Right? So it's deliberate why there's no behavioral complexity in his model. But I think what you're saying here is that it's not clear that in the GIS ABM field that the reason that behavior complexity doesn't exist is deliberate. You're saying it's emergent, right?
I'm not saying it's emergent. What I'm saying is the vast majority of models use simple threshold calculations, or simple,
Is it deliberate? Are researchers in this area
I think they're just not aware of it. Like, how many of you guys are aware of BDI and PEX? All of you should be, because you've all done classes with us, right? But you didn't put your hands up, so that's great. You see what I'm getting at here? Does it even cross your mind ever to just think beyond thresholds. And then
I thought about it.
you thought about it? Have you implemented it?
I did in Bill's class.
Yeah.
And I'm
You
trying
said
to do it in
has
my
it
model.
crossed your mind? Like it did.
Yeah.
Cross.
So, you know, the question is, do you want to build more complex models? Yes, simple models are great, but are we missing something by not going further down and making them more behaviorally complex?
Would you know the difference? So
We
this is
don't
another-
know.
w-
And
w-
this comes back to another issue,
Yeah.
which I'll talk about in a bit. Which is
Validation.
no, not validation, but ensemble model, like putting several models together and testing, exploring the same issue. Right?
Sure.
How does that you know, we don't do that neither. But you won't know, does it have an impact unless you program it different ways. So while I'm not standing here, Nick, Allison and myself are writing this book about GIS ABM, and we actually playing around with developing the same model with the PEX, the BDI, fast and frugal, and threshold calculations to see if it actually makes any difference or not. And we don't know yet, we haven't finished it.
Okay.
But you know, the underlying process is going to be different, and the motivations behind why agents do what they do is going to be different. You know, which framework or way of going about modeling behaviour it's going to be. Go on. And this is sort of the same table as you had before, but diagrammatically, thing, which is like the application area. What do we choose to be the individual? So in general, as we go down the scale here, so this is fine scale models to more aggregate models. As we go down, we'll go from individuals down to households, to institutions, to the city itself. So sometimes in certain models, you have cities as the agent. The vast majority of these models are all mathematical threshold-based calculations. And this is sort of a random sample, by the way, just from the literature. The spatial scale, the temporal scale, and here's something that's really quite interesting. What do the papers specifically mention verification and validation? And I'm not talking and do they mention calibration? And what I found really quite interesting was not all papers mention how they verified the model. Not many mention. Some do, some don't mention validation. If they do mention validation, they don't necessarily say if it's qualitative or quantitative validation. And very few agent-based models sort of mention calibration.
Over at Old Dominion, where the Swarm Fest was held this summer,
Yeah, yes.
they were not even using the word calibration. Nobody knew what that meant. Because I think they were considering validation to be both validation and calibration.
But no, because then you also you bring in calibration is on a step to validation, right?
When I said calibration, nobody knew what I was talking about.
Well, what was really interesting here was, when I was doing this, I was also looking at my co-authors' papers, and they fell into this trap. They didn't mention verification or validation in their papers, and I might have fallen into it once or twice as well. So it actually is a learning experience. That's why when I read your essays, and I might get annoyed that you don't mention verification or validation, and you know, and calibration, great if you have the data to calibrate it against, or validate, or data to validate against. Yeah, Kira.
Could you give an example of a strong calibration,
What do you mean?
like in one of these papers, where you have a yes mark?
Oh, so Benison's paper is a great one. So Benison's paper is one of my favourite papers. It's about residential location decisions in a place called Jaffa in Tel Aviv, right? And in that model, he had data from 1955 to 1995 of every individual household, right? Who lived there, what their ethnicity was, and so forth. And therefore, he used part of that data set to help calibrate the model to predict what the patterns of segregation would be in 1995.
So could calibration, though, if you have data from two different time periods, though, could you calibrate to the initial data and then validate with the second set
Yes.
of data then?
So the land use and land cover change models, like the urban growth models, like the cell-automata models, do exactly that. You might, because normally you have remote sense imagery. Now remote sense imagery goes back. Landsat goes back to the 70s, right? Or something like that. You know, you have these long periods of data sets, so you can, you know, calibrate your model to a certain point, run it forward, and then validate it against the current pattern. Yes.
For something like if you're looking at like pedestrian movement, would you so the calibration there, if you had data that would show you generally where people migrated to, would you have to calibrate an algorithm then for movement?
No,
and
you
then validate it?
You always take it. So normally with respect to validation and calibration, you take a subset of the data to calibrate it on, and a subset of the data to validate it on. Does that make sense?
Yeah, got it.
But basically, some people do a good job at validating, talking about these things. Some people don't, and I find that that's also for me an interesting area, reason for that. So let's say so Nick, one of the co-authors here, he does a lot of interesting things with crime and things like that. And when he's doing these types of models, he creates a PEX model, right? And this is where I get my notion of PEX build. That's why I like it more than fast and frugal.
Okay.
He basically has information on how people navigate through the scene. He knows about travel patterns, about people moving through this, and then the decision making is like, do I need to burgle? Do I have enough resources, i.e., enough money to buy drugs or whatnot? Where do I want to burgle? How do I travel there? How do I walk around that neighborhood? And then choose a certain burgle agent to burgle. So this is like leads, and this is sort of the data he has to help understand movement of people through the environment, and footpaths and things like that, where the houses are, and things like that. So, so we can build detailed models of basically geographical complexity with more richer behavioural frameworks in. I'm not going into detail on the PEX model of this paper or any PEX model, because after like 10 minutes I'm bored, and also they're relatively hard to explain. That's the other challenge of those types of building more complex models. But the question is, how complex a model do you need to create? So Joe, this goes back to your comment, which is, there is a debate about how complex a model should be. Should you do the KISS principle? Should you do the descriptive, keep it the KISS principle? But either way, I think you need to the complexity versus complicatedness of the model needs to be balanced, and you need to justify why you chose one over the other. Is it always the issue of parsimony? The simplest model is a better model, or is it because you're trying to build something, or not, you don't really know how it works, so you keep everything very, very simple? If you add more and more details, are you making the model any better?
What about biological models? Neural networks and machine learning embedded into the cognition, the
but then
brain of the...
you have machine learning on neural networks, these are black boxes, right?
But there's a chance that they could...
Yeah, but how do we know? We have no idea what's going on inside of them. So that's my understanding.
Well, alright, so maybe a bad example. What about like Bayesian, for example? Bayesian graphical models are very clear understanding and very clear representation of what's going on if we use something like that.
But they are not being often used in this area.
No, they're not.
So it could be worth exploring, but I don't know enough about that to tell you one way or the other. And then there's another paper, is this David O'Sullivan wrote this nice book chapter, also in the book that we did. So asking, what is it worth really building complex models? What's the utility of building really complex models versus really compared to simple models? And there's a balance between understanding and prediction. Some people just want prediction. Half the people that come to us, what do they want? They want to predict what's going to happen in the future. The other people might want to understand what might happen, or things like that. And it's a balance, trying to get one or the other. So, but to build a model that's more complex, and also potentially more useful for, say, prediction purposes, there's an effort there. There's this, you talk about the sweet spot of modeling, the Medway zone, some pattern-oriented modeling. That's sort of where you want to get at, not necessarily the really complex side of the modeling.
Are you talking about behavior here, or resolution?
A bit of everything.
The example that comes to mind from the DARPA work is slums.
Yeah.
And I don't see how you could do something simple to model a slum and then validate.
No, okay, so yeah, no, you can keep a very simple slum model.
Mm-hmm.
So, for example, Mick Patel did this slumulation model with us, right? In that model, the agents were very simple entities. They just had, they couldn't starve, so they had to go out to get food.
Mm-hmm.
They had to live somewhere, so they had to rent a location, right? So that's a very simple model. There is no real explicit geographical information in that model. There's no real family structures in that model. There's no networks or anything like that. So, I guess what I'm trying to say here is, with case or this type of idea of how complex the model should be, it's not just necessarily for prediction purposes, but how much information do you want to put into it? How much details would a mixed model be better if you added more and more variables to it? Probably not. But if you want to do something with respect to forecasting or validation, you need to add more and more stuff to that model. But with slums, you also need the data, which is also a thing that's missing. And my pet favorite thing, I should start asking this question in PhD defenses more often, which is, the two main problems potentially with agent-based models, especially ones with spatial types of models, is the idea of calibration and validation. But then the question is, what are we trying to validate and calibrate? Is it identifying, representing, and evaluating key behaviors, or the final process or pattern that comes out of the model? So I've already just said that, so never mind. But so in general, when you evaluate a model, what are you trying to evaluate?
Whether it depends on the model, but generally, like whether it reproduces reality is.
But normally though, only at the macro level, right?
Yeah.
Now, what about the micro level? Very rarely do we do, Rob's level 3 modeling, as he would talk about in his Understanding Our Creations from 1994, right?
Yeah.
Very rarely do we actually understand both the micro level validation and also the macro level. But then how do we know that the behaviors are correct? We might get the patterns right, but how do we know that the behaviors that we specified are correct in this model? Or is it just one candid explanation for this? Sorry, this is like my thoughts for the last few months in this PowerPoint deck. So it's, this is, these are things that we're currently like trying to grapple with. How should we validate? What metrics are we trying to use to validate the model against? Is it a matter of the spatial extent? Is it per, if you have an area divided up into cells, is it per pixel or per cell, or is it just the whole area in general? A lot of models will validate at a higher resolution. Therefore, they're not not on a cell by cell basis, but just out of 100 cells, we know that 20 are urban. So if my model produces 20 cells that are urban in these 100 cells, yeah, that model's valid. Or are you trying to precisely say these 20 cells exactly in these locations? That's another way, and a lot of people like play around with this.
I drew out a question actually.
Yeah.
As I was asking about calibration before, one of the things that I was thinking is with my question about like migration patterns versus just like calibrating to like a demographic data set versus calibrating an algorithm. Where do you stop? Like and how much calibration is necessary? So if you're looking at
when you say calibrate an algorithm, what do you? I always think of calibrating a model or simulation, not as necessarily an algorithm. Are you saying an algorithm is a model?
I guess I'm saying calibrating the behavior within the model.
Okay.
So if you're looking at something like migration patterns, and if you want to be able to realistically forecast where people are moving to, then I would think that you would want to in some way calibrate to previous data, which
Yes.
was looking at
But then you have to also.
migration
But here's
patterns.
the
So
ne-
there's some sort of underlying behavior algorithm for how each.
Yeah, and also what theories, there's also theory there, such as this intervening opportunities theory, which is where basically you might be want to go from A to B, but as you're going from A to B, you go to C, and C is like, oh, that's not so bad, I'm staying there. So you have to also account for those types of factors in that model, right?
Right.
But you also have to assume that the migration from one time frame would be the same as today's time frame. So, for example, many years ago, if I wanted to go from east coast to west coast, right, migration-wise, I would have to I would either have to go on horse and cart, right? Therefore, if I was using that time frame to calibrate today's time frame, where I can jump on an aeroplane, it's different. Sorry, I thought I would be finished by now. But yes, I agree. You need to
Where do you
build.
stop?
Is that a baby crying?
Sounds like
Not mine though. That's good. So we're going on this. Yeah. So going back to your question about calibration, I think it's also at what spatial scale and temporal scale do you want to do this at? Because remember what happened in the past, and it doesn't necessarily it's going to happen again in the future. So, for example, the invention of the car changed the way urban cities grew. So, if you calibrated a model before the invention of the car, it'd be very different. The growth pattern would be very different to what it is today. Or financial markets and so forth, right? They always change. The other thing is, because we're not potentially not doing a very good job of calibrating and validating our agent-based models, does that therefore impact its use in policy? So, I spent a couple of days looking at where has agent-based models been used to inform policy. I wrote a blog article on this. So, but you know, you had the BIOS group from San Jose did a lot of work for Southwest Airlines. There's Bonaboo, the guy from Ecosystems. He wrote several papers about how basically, you know, the lines at Disneyland are basically and you can bypass them lines as a result of an agent-based model. But you know, there's very few publications out there specifically saying how agent-based models have been used to impact policy. Right? Why is that the case? And I'm still struggling with that. Is it because no one wants to sell the secret sauce, or no one's publishing and writing about these things?
But I don't just think it's that. I mean, I think if you're using an agent-based model, again, I think you're at a point where you're just not using the full force. You're not doing the validation. You're not doing the calibration. So your models are failing, and I don't think people are continuing it. They're not interested after they try. They're not interested, and they think it's because the framework or the methodology is flawed. But it's usually because they just haven't done it right.
Yeah. So we're doing a poor job of evaluating the models. Are you saying?
I think so.
Jolly good. I like how you with my bullet points.
Yes.
But yeah.
It could also be, I think it could also be like the no confidence level, because I was taking a class with somebody who worked in the military for some big general, and Tom will tell you what the ranks are. I don't know. And he said that for the most part it becomes very hard convincing these people that we're able to simulate in real life these things. Like, it looks pretty to move things around and have all that going, which is great as far as you want to say this is what we're predicting. When you make it into policy, it's harder.
Yeah.
But haven't European governments or organizations like done a better job of using ABM than the US? It was like OECD uses it, and I was like looking at this climate change while we were looking at, and it's a report on insights for climate change policy from agent-based modeling on land use by OECD. So
it's a report though. Does it actually?
No,
have
it's
it
adaptations.
But has
and
it therefore?
use.
But has OECD or whatever
Yeah.
used that to therefore change their policies?
Oh, yeah, that
You know.
I will need to read it because I'm looking it up while we're talking.
Anyone
but-
finds those types of papers, please send them my way. I would actually appreciate that.
Yeah,
Data is also an issue. We need data for everything with respect to designing the model, building the model, evaluating the model, and then once we gain some confidence in the model, either exploring or predicting what might happen in the future, right? So we need data, but data's hard to come by, especially with respect to human behavior and things like that. And I'm looking at time, and I'm not going to keep you guys till 4 o'clock, so basically we need data for models. And anyone wants slides, I can give you that. So, have we progressed much about data or behavior in the last 20 odd years? I think we have to some extent. We are now witnessing models more behaviors in models, especially using these frameworks, which is nice. The models are also, I think, to some extent getting more complicated and using more and more data. Sorry, when you give me that look, I'm curious.
No,
No.
I'm just thinking.
No, think about it. Like 20 years ago, these models, like sugar scale models, there's no real data in them, right?
Right.
Now we are, incorporating data such as distance to shop or distance to a thing. We're incorporating information, synthetic populations when it comes to creating the agent-based models, based on census information. We're now adding social networks. The bugger about talking on a Friday seminar I'm discovering when working with certain faculty members here, like Bill and Annetta, is I can't talk about WMDs and I can't talk about crises because you two have talked already about them. So that's another rant of mine. But where were we going on this? But
More behavioral.
yeah, no,
behavioral.
you had a question.
Well, I mean, this is kind of self-serving. 'Cause this is what I'm looking at right now. But and I'm talking with Jackie Cahill, is would it be beneficial, or actually look at something like some of the machine learning stuff like scikit-learn, and it'll have dimensionality reduction, K-clustering, and linear regression, and all that stuff, where you have like but I can't find like say agent-based library. It's like, okay, we're gonna look at how and agents form coalitions, or agents do this economic behavior, whatever. So it's not necessarily building all these algorithms of behavior underneath from scratch, but they have a library like an API where they could just pull it in, and then the kind of mix match behaviors together to try and
So several years ago we wrote this key challenges paper, and one of the challenges there was like reproducing code, right? But I think now that sort of challenge is being done, right? People with GitHub or sharing on Open ABM, things like that, we can start doing that. But no one shares code. No one really reuses code or creates code to be reused by other people. And I think that's still a challenge. So yeah. So I didn't. But yeah, calibration is still an issue. I think within these things. A lot of time the spatial interaction modeling styles of models, the migration models, tend to be more calibrated and easier to do. The more accurate the model, the easier it is to calibrate. It's generally the case in these types of models. And then is there an easier way to build better? Is there a better way to build better models from a geographical perspective? Could there be a solution to this problem? Big data. I do love that slide.
I've seen this slide in every presentation you've had.
Really?
It's really cool though.
So, I said we're trying to deal with geographical spaces. These geographical spaces are messy. We are very good from GIS. I already said, we are very good at building the terrain. We are very good at mapping things and all this type of stuff. We are just starting to explore the social connections in respect to geographical spaces. Social networks and so forth, yes, have been around, but the social networks that you play around with, say, Joe, are not very spatial per se, right? So therefore, how does space impact these social networks is something that's quite interesting.
But I'd say that space makes the networks easier because you're working, if geographic networks are at a lower dimension in the 1, 2, and 3, where social networks can have extremely high dimensions.
I would say
it
that
simplifies the problem.
No.
So
No. And then you over connecting all these different networks together as well. That's the other thing. But that's another talk, another thing. And also, how do we move through these spaces is what we're trying to get at. So, I think big data can help get to these social spaces and also the relationships between these spaces. This is where I see the big data role. This is not big data. More and more remote sensing, stuff like that. That's just GIS. We've been doing that for years. This is what the big data, the streaming data sets and things like that. Oyster card, your what do you call the Metro card that you have in DC? Those tap in, tap out. We have lots of new data sets we can explore about how people move through the environment, who they interact with, who RFID tags. We can look at say who tweets, who travels down to King's Cross in London, and where do they come from. So this is like basically, based on Twitter data, we can get where people live, where people work, patterns through Twitter, social media data sets, or if you have GPS traces from cars, fleet data and stuff like that, we get migration patterns, movement patterns and things like that. you know, you also got this digital exhaust. Ask me about bias in social media. Well, you know, of course you're going to have bias in social media. Sorry, this is a rhetorical question. Don't ask me about bias. But, you know, everything's got all data has some type of bias, and we need to be aware of those types of things. There's like this tweets coming out of Leeds in New York City that Nick made. The other thing is, you know, we are very good at getting aggregate data, such as age, sex, and things like that from surveys, censuses, and things like that. Can we use social media, big data to help understand people's opinions, attitudes, actions about things, their mobility patterns? Can we fuse those two together to understand basically who, where, and what do people do, and why do they do it? And I'm thinking, yes, we can, but you know, we need to keep exploring these types of things, I think. You know, and with pedestrian models, now with respect to, we have CCTV cameras, RFID tags, things like that. We can track people's movements. We can use that type of movement data to help calibrate pedestrian models, how people move through a space. So this is basically that green dot that you see of pedestrians moving through a space, and that's their like trails that they are leaving behind them, right? How good is that model of people entering and exiting this scene? Well, we can say, you know, based on trajectory data, we can then say, well, this is the, you know, and this is the model. We can then sort of gain some confidence in our model if we're producing the same types of patterns, right? So that helps with the calibration. And therefore, if we understand how people are moving through the scene, we can then ask the question, what happens if you put an obstacle here? How will people move around it? If you're already capturing the right patterns at one level, hopefully by adding an obstacle or something like that, you can ask the what-if questions within these types of models. Sarah Wise did basically hotspot models, evacuation models during a natural disaster. How do you know how people evacuate? Or how do you know that the migration path that she's predicting people will take during a wildfire event? You know, if her model's predicting that basically people are going to be migrating along, or there's going to be heavy traffic along these roads, or and things like that, does the social media data, Flickr photos, anything streaming, show where these traffic jams are occurring, or do they give you insight into the current conditions in the area? Is that area flooded? Is there, you know, can you drive along that road and so forth? So Sarah Wise was playing around with basically using social media data to validate her agent-based models. Is R squared the best way of analyzing models, or is there other ways? I'm not going to sing. What I'm more excited about, this is like the holy grail, I think, is the idea of a simulation modeling. You build a model, you run the model, and then you infuse that model with new sources of data. As more data comes in, you refine your model, and then see how that basically impacts, therefore trying to forecast what might happen in the future using up-to-date information. I don't think we're there yet, but I think we are getting more and more data, and we're having these shorter scale processes, pedestrian movement, traffic models, and things like that. We can use the data simulation methods to therefore forecast what conditions are going to be like in the short term. And I say short term because I think a lot of the big data sets have only been around for, you know, tend to be short term in sense that relatively recently accessed, not like census data that goes back hundreds of years. Now pet peeve. Now another thing that's quite interesting at the moment is that weather model. Everyone likes watching. Everyone follows Capital Weather Gang. No,
Yeah,
reads
yeah.
Washington Post.
Yes.
They do, I think, great job of comparing their European model versus the US model, right? With respect to, you know, what the weather's going to be like. We don't do that in the social sciences. So you might have, you know, if all your models converge on the same type of pattern, you know there's going to be like relatively low uncertainty in what's going to happen. You know, this is roughly the path of the hurricane. However, if the hurricane's going all over the place and your models are suggesting it's going all over the place, how do you know which one's going to be right? Right? So the idea is, can we start creating ensembles of models? Can we start looking at the same social phenomena and compare them all together and try to understand, you know, what's good, which sets of models are good at producing or forecasting the future? We haven't even. That's something that we're not even tackling. We're creating these one-off models, and that's it. I think one area of interest would be to start creating models looking at the same phenomena, like it's, to some extent like the disease models have done with the Ebola outbreak. The Waldrop article, is it Mitch Waldrop? The one in the PNAS recently, how people were all looking at the same problem, and then you can compare the models together and see, find out areas of uncertainty within model ranges. Why is that uncertainty there? You can only do that if you start looking at the problems through an ensemble approach, I think. But we are a long way off from doing this. But ideally, that's another area I think we could play around with. That would be very nice. And to finish, from a geographical point of view, what have we done? What have we accomplished in the last 20 years? We have more agents, more complex behaviors. We have more data being used in models. We have nicer tools, software, visualization options, and lots of applications for these types of models. Where have we not advanced very much? I still say, like people talked about right in the 1990s, the issues of calibration and validation of these models. I think there's been little advancement here, and also, apart from we're very good now at representing the spatial world around us, but we're not very good at doing anything, I would say, validating anything more beyond that. Also, I think there's little, how it has been implemented in policy, I'm still hard to understand. What should we be doing now, in the future? What are the next 20 years? I think we should focus, better models of human behavior. Potentially this dynamic assimilation would be nice and interesting to do. Also, the issue of exploring calibration at different spatial and temporal scales, and also potentially ensemble modeling. I think those are areas that could be quite interesting to explore in the next 20 years. Anyway, thank you very much, and I'm sorry for keeping you after 4 o'clock. Any questions? Jolly good, thank you.